Hi everyone. Today my teammates and I will be presenting this paper titled Learning Transferable Features for Implicit Neural Representations. So let's get started. So implicit neural representations are a type of function-based representation that encodes signals like images, videos, or 3D shapes using a continuous function rather than discrete grid-based storage of pixel values. So instead of storing an image as a matrix of pixel values as in traditional representation, an INR defines the image as a function f theta that maps input coordinates to output values. So the function is typically parameterized by multi-layer perceptrons. In the next slide, I'll be explaining about what exactly a multi-layer perceptron is. So INRs encode signal as weights of an MLP or the multi-layer perceptrons. The model learns a function that can reconstruct the original signal when queried at any given coordinate. For example, a 2D image INR receives XY coordinates as input and outputs RGB values. A 3D shape INR takes XYZ coordinates and outputs sign distance values. Typically, a video INR takes XY and time coordinate and outputs RGB values over time. So, multi-layer perceptrons are the fundamental building blocks for implicit neural representation. It is a type of artificial neural network composed of multiple layers of neurons, where each neuron applies a weighted sum followed by an activation function. So, MLP consists of multiple layers. Input layer, which takes the input features, as in case of images, it takes the pixel coordinates, and the hidden layers performs the transformation using weights and activation functions. The output layer produces the final result. So the multi-layer perceptron can be mathematically represented as f theta, which takes xy as the input spatial coordinates and which outputs the RGB as the predicted color values at those coordinates. So this MLP learns the mapping function f theta to reconstruct the original image. By optimizing the weights of theta, the MLP can learn a continuous function that represents the signal. And activation functions, they just introduce non-linearity to the network, which enables it to learn complex patterns. So INRs have several advantages over traditional representation. So unlike traditional grid-based methods, INRs do not rely on fixed resolution grids. They can be evaluated at any point in space, which enables infinite resolution. Storing an INR requires only a small set of MLP weights instead of a large matrix of discrete values. And traditional neural network often struggle to reproduce high-frequency details. INRs, particularly with siren activation function and Fourier features can effectively capture fine textures and edges. And INRs can learn the structure of natural signals like images of 3D scenes, which makes them effective for inverse problems, super resolution, and denoising. Since an INR stores data as a function instead of a grid, it enables highly compact signal representation. This is particularly useful for neural compression, where storing the INR weights is more efficient than saving raw data. And there are few challenges with this approach as well. Uh, INRs are designed to fit a single signal, so every new signal requires a separate training process from the scratch. This is inefficient compared to deep learning models like CNNs, which can generalize across data sets after pre-training. And INRs learn by mapping input coordinates to output values. So during the training, they tend to overfit the spatial gradients, meaning they capture very fine details of a signal instead of general patterns. This makes them great at memorizing a single signal, but very poor at adapting to new signals. So, unlike CNNs or transformers, INRs do not naturally transfer learned features across different signals. So each INR must learn features from scratch rather than leveraging previously learned representation. This limits their use in tasks that require learning across datasets such as inverse problems or multi-way 3D reconstruction. Like a CNN trained on thousands of images can classify new images, but an INR trained on one image cannot classify another image without retraining. So that's one particular problem. So as I told in the previous slide, traditionally implicit neural representation are designed to fit a single signal. While they achieve high quality result, they lack generalizability, meaning that every new signal requires training an INR from scratch. This leads to increased computational cost, where each new signal requires a full optimization process and limited efficiency. Even if the new signal is similar to previously seen data, the INR cannot transfer its learned knowledge. And many applications such as denoising, super resolution, and inverse problem require leveraging prior information, which traditional INRs cannot do. So, if INRs could transfer learned feature across signals, they would reduce the training time by reusing learned representations. These new signals could fit faster, and prior knowledge from similar signals can lead to a better initialization. And also, INR models could encode general structure from a domain, helping in downstream tasks like image restoration and 3D modeling. So, the authors propose a new technique called strainer architecture. Strainer is designed to introduce transferable features into INRs by using shared encoder and decoder architecture. So, instead of training each INR independently from the scratch, Strainers separates the INR into two parts: the shared encoder, which learns the common features across multiple similar signals, and independent decoders, which remain specific to each individual signals. So the encoder captures the general representations that are useful for the multiple images or signals. The decoder remains independent, allowing it to specialize for each new signal without affecting its previously learned knowledge. So by using learned representation, Strainer enables faster convergence. The encoder is already trained, so the model needs fewer iterations to adapt to a new signal. And also, new signals benefit from previously learned structure, and it also improves the quality. Like pre-trained encoders provide better initialization, which helps in avoiding poor local minima during the gradient descent phase. And so that's it. And Shreyas is going to take over from here, where he'll give an in detailed explanation of the architecture.
Hello everyone. Today I'll be presenting the technical methodology and architecture of Schreiner, a novel framework that enhances the transferability of implicit neural representations or INRs. We'll explore its structure, training process, and why it outperforms traditional INR training methods. So, Schreiner is an innovative INR training framework that introduces transferable features for more efficient learning. Traditional INRs learn each signal from the scratch, which is inefficient. Schreiner shares encoder layers across different INRs while keeping the decoder layers independent. This approach allows new INRs to leverage previously learned representations, speeding up training and improving reconstruction quality. The key innovation in Schreiner is its encoder-decoder structure. Shared encoder layers, these generalized features, these learn generalized features across multiple INRs, allowing knowledge transfer. Independent decoder layers, these ensure each INR still maintains task-specific flexibility. This structure allows Schreiner to reuse useful features, improving generalization and efficiency. Schreiner's training involves three key steps. We first train multiple INRs with shared encoder to learn common features across different signals. The encoder captures transferable representations while decoder remains signal specific. At inference, we use the train encoder as initialization for a new INR, enabling rapid convergence and improved performance. Let's expand on how Schreiner learns transferable features with a more detailed explanation. So first step 1, training multiple INRs with a shared encoder. Unlike standard INRs that learn each signal independently, Schreiner trains a group of INRs together. The encoder layers are shared across all INRs, meaning they extract common features from multiple signals. The decoder layers remain independent, ensuring that each INR can still adapt to individual signals. Why this works? Instead of learning a specific signal, the encoder now captures general patterns across signals. This allows the model to retain useful features and reuse them later for unseen signals. Step 2, encoder capture transferable representations. Once trained, the shared encoder now contains features that generalize across similar signals. For example, if the encoder has been trained on multiple images, it will have learned representations for textures, edges and contours, color distributions, and geometric structures. These learned features persist and can be used in further INR training. Why this works? The encoder has already seen multiple variations of signals, making it robust. Instead of learning from random initialization, future INRs can start with a well trained feature set. Step 3, transferring features to new INR training. When training a new INR, Schreiner initializes it using the pre-trained encoder weights instead of random initialization. This means the INR doesn't have to learn low-level features again. It only fine-tunes for the specific signal. The new INR thus learns much faster and with better accuracy. And why this works? The model representation has a strong feature representation, allowing it to focus on signal specific details. This results in faster convergence, higher reconstruction quality, and more robust performance in inverse problems. So let's compare standard INR training with Schreiner's method. Standard INRs from uh, random initialization for every new signal, making training slow. Schreiner, on the other hand, reuses pre-trained encoder features, allowing new INRs to start from an advanced state. This significantly reduces training iterations while maintaining high reconstruction fidelity. So, this summarizes Schreiner's advantages over INR training. So it shows faster convergence plus 10 dB improvement in signal quality early in the training and faster training time since knowledge is transferred instead of learned from scratch, higher reconstruction accuracy, especially in complex signals. These results demonstrate how Schreiner makes INRs more efficient and scalable. And in this image, we show the reconstruction quality PSNR of different initialization schemes for in-domain image fitting of on celeb A HQ. We compare siren model initialized by random weights and uh, fitting on end of phase image that's siren fine-tuned and Schreiner 1 trained using one phase image, Schreiner 10 trained using 10 face images. We also evaluate against multiple baselines such as MetaLearn 5K, TransINR, and IPC. Here we can see that Trainer learns faster. So in this image, during training time in image A, Schreiner divides an INR into encoder and decoder layers. Schreiner fits similar signals while sharing the encoder layers, capturing a rich set of transferable features. At this time, Schreiner serves as powerful initialization for fitting a new signal. And image B, an INR initialized with Schreiner's learning encoder features achieves, as you can see in C, a faster convergence and better quality reconstruction compared to baseline siren models. So in this image, uh, you can see visualization of learned features in Schreiner and baseline siren model. We visualize in image A the first principal component of the learn encoder features for Schreiner and corresponding layer for siren. At iteration 0, you can see that Schreiner features already capture a low dimensional structure, allowing it to quickly adapt to the cat image. High frequency details uh, emerges in Schreiner's learn feature by iteration 50, whereas siren is lacking even at iteration 100. The inset showing the power spectrum of reconstructed image further shows that Schreiner learns high frequency faster. We also show that in image B, the reconstructed images and remark that Schreiner fits the higher frequencies much faster. So, Schreiner introduces several key benefits. Faster learning by leveraging the pre-trained encoder, features dramatically reduces training time. Higher reconstruction quality by using shared representations. Schreiner enhances signal fidelity. Better generalization. Schreiner's transferable features allow it to adapt across various tasks in image representation, 3D modeling, and inverse problems. This makes it a powerful tool for neural rendering, image compression, and real-time scene reconstruction. So, to summarize, Schreiner transforms the way we train INRs by introducing transferable features, making training faster, more efficient, and more accurate. Next, we will explore experimental results and real world applications to see how Schreiner performs across different tasks.
Now I'll explain the experimental results which we have done in this paper. So in these experiments, we use the Siren MLP with 6 layers and sinusoid nonlinearities. Like they have considered two versions of the strainer. One strainer is with one decoder where the encoder layers are initialized using a shared encoder trained on a single image, and the another strainer 10 that has 10 decoders where the encoder layers are initialized using the shared encoder trained on only 10 images. So the baseline used for the is a siren a vanilla model with random uniform initialization. The data sets used for these experiments are mainly used are the celeb AHQ. Then we have the animal faces HQ and the Oasis MRI for the experiments. And they have divided the celeb AHQ data set into 10 train images and 550 test images. For the animal faces HQ data set, they have used only the cat data and used 10 images for training and 368 images for testing. For the OSS MRI dataset, they have used 10 of the 2D raw MRI slices for training and 144 for testing. They've also used the Stanford cards and flowers to validate out of domain generalization and Kodak true images for demonstrating high resolution image fitting. So Strainer enables plus 10 dB faster convergence compared to standard INRs. These traditional implicit neural representations, that is the INRs, require training from scratch for each of the signals, which can be computationally expensive and slow. Strainer introduces a transferable feature learning framework, allowing models to converge significantly faster. This results in an approximate plus 10 dB improvement in PSNR at early stages of the training compared to the standard siren models. Rapid convergence means better quality results in fewer training iterations, making strainer ideal for real time or the resource constrained applications. So the next is the strainer improves INR initialization and representation quality. So instead of starting from the random initialization like traditional INRs, trainer uses the learned encoder features from similar signals. This pre-trained initialization helps the INRs achieve higher accuracy in reconstruction with better feature transferability. The shared encoder structure that ensures that INR models can learn richer representations that generalize better across different datasets. As a result, strainer maintains high reconstruction fidelity with less overfitting and more efficient learning. So here we have the graph shown. So this is a performance comparison of strainer versus siren in PSNR improvement. So we can see there are this is trained on 10,000 on 1,000 iterations, and we can see the gradient versus iterations graph over here. So we can see strainer consistently outperforms siren in peak signal to noise ratio in domain versus out of domain generalization. So in domain is a scenario where the model is trained and tested on data from the same distribution. For example, if a strainer is trained on Celeb AHQ dataset, that is the face images, and tested on new face images from the same dataset, then that is a in-domain generalization. So the model when the model is trained on this the generalization, the model benefits from seeing similar features during training, leading to higher accuracy and faster convergence. Now, on the other hand, out of domain generalization refers to a scenario where the model is trained on one data set but tested on a different distribution. For example, we can consider training strainer on Celeb HQ, that is the faces dataset, and testing it on animal faces HQ, for example, cats, or OSS MRI, like medical images. So this will test the model's ability to generalize beyond what it was explicitly trained on. A strong out-of-domain performance means the model has learned transferable features that work across a diverse of data types. So in-domain performance. So strainer significantly improves image fitting performance by providing a strong initialization. Traditional INRs require training from scratch for every new signal, making them very expensive computationally. Strainer also, however, leverages learned features from similar signals, allowing models to start with a better foundation. So this will result in higher PSNR, that is the peak signal to noise ratio, from the early training stages. So it means that it will be sharper and more accurate. It will have more sharper and more accurate reconstructions. So compared to the baseline siren and meta learned INRs, strainer converges faster and more effectively to high quality results. So for out of domain generalization, so one of strainer's most powerful aspect is its ability to generalize beyond its training data. So unlike the regular INRs or the conventional INRs, which struggle with unseen distributions, strainer's transferable features allow it to adapt well to new and the diverse data sets. So this has been tested across the Celeb HQ dataset, the AFHQ dataset, and the OSS MRI dataset, proving its robustness in all the different domains. The strong generalization suggests that the potential applications in cross-domain INR training, where a model is trained on one dataset, can effectively adapt to another. So here we have the table showing the comparison of PSNR gains across in-domain as well as out-of-domain datasets. So so we can see here that strainer achieves a much higher initial PSNR and maintains an edge across the other multiple datasets. So this confirms that strainer is not only faster but also more versatile, making it a scalable solution for various applications, such as we can consider like real-time rendering, then medical imaging or 3D modeling. So here we see these values which are different. So like PSNR values for across different methods for the learning implicit neural representations, that is the INRs on various data sets. So the celeb AHQID, so like this is a trend in the in-domain generalization. So this is the model's ability to fit in-domain images, whereas the AFHQ and OSIS MRI datasets are used for out-of-domain generalization. So um, so the proposed method here, that is the strainer 10, so it achieves the highest PSNR in all the data sets. So we can see that the for Celeb HQ it has achieved 57.80. For the AFHQ it has achieved 57.46, and for the OSIS MRI it has achieved 59.50. So even the strainer 10 trend on the flowers as well as the Stanford cars data set has an performs well on those data sets as well. So here we can see that strainer 10 outperforms all the methods in PSNR across both the in-domain generalizations as well as the out-of-domain generalizations. So we can see that like we learn from here that the transformer based methods and the IPC struggle with generalization when we compare it to the strainer. We'll see the applications and use cases for the strainer methods. So as we can see that there are the strainer achieves faster and more efficient INR training on various domains. We can apply it to like considering the image compression. So strainer enhances the INR training by capturing high quality signal representations with only fewer parameters. So this will lead to better compression efficiency, and it will preserve more image details while using less storage. So it is beneficial for applications like video streaming, cloud storage, and environments where the bandwidth is limited. So image compression is very crucial in these cases. So the next one is 3D modeling. So the efficient implicit neural representation for 3D scenes. So traditional 3D scene reconstruction techniques, they require extensive point cloud data or like the mesh representations. So Strainer provides faster and more accurate representations for the 3D objects, and this enables applications in virtual reality, gaming, and digital twin modeling. So the ability to generalize across different 3D structures makes this a valuable tool for real-time 3D rendering. So the next application is medical imaging. So faster convergence for MRI as well as CT reconstructions. MRI and CT scans are very computationally intensive to process because of their high resolution nature and noise levels. So strainer's fast convergence properties allow for quicker and more precise reconstructions. So this reduces the scan to diagnosis time. This has potential to significantly impact low resource settings where the computer power is limited. So inverse problems enhance super resolution and denoising capabilities. So inverse problems involve reconstructing high fidelity signals from incomplete or the noisy data. So strainer in this case acts as a strong prior that will accelerate super resolution. That is the recovering high resolution images from the low resolution inputs, and denoising, which means the removing artifacts and noise from images. So this makes strainer very useful in applications like satellite imagery or the medical imaging and computational photography. So these applications show us the strainer's versatility, and also its ability to enhance in multiple domains. Next is the conclusion now. So here we can see like a summary of what we have learned today is strainer successfully learns transferable features across image distributions, which leads to faster and more accurate image reconstruction at test time. Strainer 10 achieves the highest PSNR and SSIM scores, outperforming the baseline methods or models like Siren and fine-tuned Siren by 7 to 10 dB. It demonstrates strong generalization across different domains and datasets, including the Celeb AHQ, Animal Faces HQ, and Oasis MRI datasets. And it extends well to out-of-domain tasks. So the performance and generalization of strainer. So it effectively strainer like effectively recovers fine details in as few as 100 iterations, highlighting its efficiency for medical imaging and inverse problems. So pre-training on a Celeb AHQ dataset improves MRI reconstruction, showing that strainer captures broadly useful image priors. It also generalized well to high resolution images like those in the Kodak dataset, proving its scalability. Um, Efficiency and the training speed. So strainer is significantly faster and more computationally efficient than the meta-learned 5K method or the transformer methods like the trans-INR and IPC. So it achieves strong initialization in just 24.54 seconds when compared to the meta-learned 5K's 20 times longer runtime. Um, so it avoids the need for large data sets and complex training routines, making it elegant and practical solution. Um, so the next steps here we see that the also the limitations will talk about it. So strainers randomly initialized decoder layers can sometimes cause instability in the form of PSNR. Uh, PSNR drops, but the model quickly recovers. The exact nature of what features are being transferred and how they compare to CNNs and transformers. So this needs a further study. Also, future research should explore how strainer shared encoder adapts across various domains and improves its stability for real-time applications. Um, Further analysis is strainer's initialization allows it to capture high frequency details faster than Siren, as seen in the power spectrum analysis. The local complexity measure suggests strainer better partitions input space for transfer learning, making it superior for in-domain and out-of-domain tasks. Unlike meta-learned 5K, which exhibits random partitioning, strainer learns structured features more attuned to dataset priors, which explains its higher performance. So overall, we can say that Strainer's potential as a fast, efficient, and generalizable INR training framework with multiple applications in medical imaging, 3D modeling, and real-time neural rendering. So that's for today. If you have any questions, you can ask.